Hey, and welcome to the 2020 much delayed third Hanrahan Lecture organised by the Geotechnical Society of Ireland and Engineers Ireland. We'll follow this with the AGM. My name is Carl Brangan. I'm a geotechnical engineer with ESB. I'm also the chairperson of the society. We're having this event as a hybrid lecture. The schedule today is I'm just going to welcome everybody, which I'm doing at the moment. Our guest lecturer will be Professor Michael Brown, who I'll introduce very shortly. Looks different on our screen to my screen. Then I'll do a quick little review of what the Geotechnical Society has been up to, and we'll break for lunch or break for coffee. And followed by that, we'll have the main event, which is Trevor delivering the third Hanrahan Lecture. I'll do proper introductions to it later. For the moment, I shall introduce our guest lecturer, Michael Brown. So Professor Michael Brown is Professor of Geotechnics in the University of Dundee. He graduated in 1995 from the University of Bradford with first class honours degree in civil and structural engineering. He then obtained his doctorate in the University of Sheffield with work on rapid load testing of piles and faults. He worked for a few years in consultancy before, my notes are, I'm sorry, I apologize, Mike. Anyway, he moved to Dundee, what year was it, sir?
2004.
From 2004, and recently became professor of geotechnics there. He's done quite a bit of work for various geotechnical journals. So he was the past editor of the Institute of Civil Engineers Proceedings in Geotechnical Engineering. He is also on the editorial, or sat on the editorial panels of Geotechnique and the Japanese Geotechnical Society's Foundations Journal, Soils and Foundations Journal. A number of his research projects include, to note anyway, our SUT, the Offshore Site Investigations Group, and he's a member of the EPSRC Offshore Renewable Energy Research Alignment Group. He's also a member of the Scottish Marine and Renewable Smart Centre, SMART, at Dundee University. I've done a very poor job of that, and I do apologise. So Mike, please come up and do a better job to me.
Thank you, Carl. So without much of ado, I'll just carry on regardless. As Carl says, what I'm going to talk to you about today is actually something that I started many years ago when I was doing my PhD, probably in about 1999, which is rapid load testing of piles, particularly in clays and things to do with rate effects. And then over time, I was quite interested in making sure these kind of things came into standardization and codification so that people in the street could actually use the methods that we've developed. So I'll move on without much of ado, he says. So what I'd like to go through today is the need for pile testing. Might seem obvious, but based on some of my experience, it's not. Some of the current practice, I think that we should be capturing, maybe if we aren't. And I think I'm talking more towards aiming for what should be in codification, for instance. Then I'll go through rapid load testing, if it's not something you've come across, and what current guidance there is and what we've developed more recently. And with a view to what's coming out in EC7, so Eurocode 7 is obviously being evolved at the moment, and we'll see a new version soon that I'm sure Trevor can update us on. Some of my thoughts and feelings about that, and then some of my personal thoughts about codification and how it should and shouldn't be used, maybe. So pile testing, I think I picked out two of the comments from Mark Randolph's ranking lecture, that obviously on pile design, particularly offshore pile design, seen as a very important paper. And it's quite interesting what he says about pile design empirical and the use of testing. So I will paraphrase, but scientific approaches to pile design have advanced enormously in recent decades, and yet still the most fundamental aspects of pile design, that of estimating axial capacity, relies heavily upon empirical correlations. And he goes on to say, it's consistent with my belief that we may never be able to estimate axial pile capacity in many soil types more accurately than plus or minus 30%. So on that basis, we therefore need to rely more and more on pile testing and refine our design methods. So that's Mark, considered one of the gods of sort of pile design, particularly offshore, telling us that we should be doing more pile testing. And then my observations based on that, people are probably more familiar with using Eurocode than I am. I'm an academic, I don't use these things. I hopefully put some bits in if we do good stuff. Does Eurocode 7 cover this range of variability that Mark's talking about, plus or minus 30%? Are our design methods then fit for purpose? And should we actually be doing more to verify them? We always assume they've been verified, but do we actually know where our factors come from and what kind of tests or what kind of piles they were actually designed for? And it is there in EC7 already, that empirical or analytical calculations should be validated against static load tests in comparable situations. So are we confident that that's ever been done in their lifetime? I think the other thing I have a problem with in this modern day, not using tests as we should, is that obviously with a view to things like sustainability, use of concrete, CO2 levels, that if we're over designing, is that a result of our empirical methods? We should be refining things as much as possible to get away from that. So in my view, pile testing real piles and construction methodologies is important. What should be forcing us that way? Is there anything that we've got out there? So obviously this is UK experience. I'm not sure if you're familiar with the ICE's spear wall, but this is where we go in the UK for guidance on pile design, specification, testing, design, etc. And they move more to a risk-based way of looking at pile design and pile testing. So if you've got low risk, for instance, you're well experienced on that site with that methodology in the same ground, then it's not essential that you're doing pile testing. But then if you're moving to higher risk situations where you've got complex ground conditions, you don't know how well your empirical methodology might perform there, then it starts to prescribe the amount of pile testing that you should be doing. So it is there in other forms of codification or local guidance, maybe the similar in Ireland, but there is in the UK. So there is a precedent for doing more pile testing based on risk levels for your site. Nothing in EC7, I think, at the moment, as far as I'm aware, to try and cover that. Also, I think Trevor would have been at this, and I think we discussed things at the time of 2016 ETC3, so Technical Committee European, on looking at EC7 and its effects to date in 2016 on how we design piles and how we construct them. And every country, apart from the UK, as I said there, they obviously didn't get the memo. Maybe they're still designing to BS 8004, but it's being recorded, so don't tell anybody. They were the only country that didn't seem to respond. Most of Europe responded to that survey about methodologies and what people had been doing and what they're doing at that time. And I managed to get hold of those reports from all the different countries. I think Ireland did a nice job. It was a nice report. But what I saw across Europe, there was little comment on the use of pile testing at all, if any, in those documents. And where there was, at least it was good, they were telling us that they were verifying analytical techniques. So there was some mention, some use, but it was relatively rare. So was there any pile testing going on? Are we using it as probably we should be? So as my observations again at the bottom there, should an evolution of EC7 been doing more to encourage pile testing? Should it have new factors or incentives or model factors if you do a pile test? Should it give you a better factor of safety effectively if you do the testing? And should there be more general guidance on pile testing? I think I remember when looking at trying to get the spec for static pile testing, and it's an ISMGE paper that nobody can get hold of, I think, from memory if you look in EC7, but maybe somebody's had more luck than me of getting that guidance. So moving on to what I'm talking about that's slightly different is my speciality, and what we generated testing standards for, or what we call rapid load pile testing. And this is different, obviously, from a static pile test, and it's very different from a dynamic pile test. And there's an example of the kind of outputs that you might see from these kind of testing. Here you can see time on the bottom. Note this is in milliseconds, and you've got a pulse of loading, and you've got the corresponding deflection as you go. So compared with a static load test that might take 3 days to complete, or a dynamic test that might be over in 10 milliseconds, you've got an event there that's about 100 to 200 milliseconds. So your pile's moving relatively fast, could be up to a meter per second in terms of deformation rates. So it's undrained and viscous, it's moving very, very fast. One of the things I'd like to point out, and as you'll see in a minute with my silly slide, is that it's very different from dynamic testing, and it's obviously very different from static testing. And there is an official definition in the code we developed, a code for testing that I'll mention later that came out in 2016. The ISO there, 22477 part 10, that's particularly for rapid load testing. So it's a very different test to a dynamic test. So just to exemplify that, we've got my elephants to show you the differences. So we've got a static test, an elephant sat on a pile. We've got rapid load testing in the middle, which is an elephant falling on a cushion. That gives you a longer test. And then we've got the dynamic testing over here. This is done by Allnamics, who produce a rapid load testing machine, and obviously they don't like dynamic testing because the pile's not very happy about bang so hard so quickly. So slightly biased, but it shows you the slight differences in what we're doing. To give you an example of rapid load test, this is a dynamic test, one of the different methods. This is a launched mass methodology. 3 different loads going on here, so you can cycle very quickly, magnitude, and it catches the mass to stop it coming back down on the pile using actuated hydraulic followers.
That was a bit more impressive, wasn't it, that one?
I think the director of cementation now, I think. When he was doing his MSc, he was on my side. So just to give you a feel for how it's built up, you see the machine on the left there. That's a 3 meganewton machine. You prepare the pile just by sticking or gluing a plate on the top. Not a lot of work to be done there, so it's quite easy. You've then got a reaction mass that you saw being thrown up in the videos. It's about 5 to 10% of that you need in a static test, because you're accelerating that upwards at high speed. So you're getting the inertial benefit. So the kit's a lot lighter than you would need for static at all. And because it's quite an interesting event, then we often use non-contact methodologies for measuring displacement. So in this case, they are shining a laser on a detector that's on the bottom of the machine. More recently these days, they use high-speed optical methods, so basically digital theodolites that track a target as technology's moved on. And we'll put an accelerometer on the static machine at the bottom, and that will allow us to have backup of acceleration, velocity, displacement as well as we need it. So you can measure things in different ways. The other thing to point out is that this sensor thing that you'll see over here, this is also a load cell. So you don't have strain gauges on the pile, you've got direct measurements of loads going on. So effectively, it's not like a dynamic test where you're having to interpret strain gauges that are on concrete that may also be another source of error. So everything's measured directly. And the Big Bang, how was that created? In the Statnamic machine, they burn a commercial fuel, as they called it. We're not allowed to call it explosives because people got jumpy when you went across borders with explosives. They're effectively mining explosives. They burn, you can burn them in your hand and they burn very slowly, but when they're constrained in the chamber that you saw there, they burn fast and they create a lot of gas. And it's basically a gas release that's forcing that mass upwards. So that's what they look like. Some animation has popped in here. They pop that in this mesh cage in here. There's a shotgun cartridge cap in the bottom. They put 12 volts across that, and that starts the process, and they start their login. And you can see the guy on the far side loading it into the Statnamic machine. And there's a load cell at the bottom of that we saw previously. There's like a piston, the weight drops down on top of that. And when the gas is burnt, it vents out the top, and that's what forces the weight upwards, and you get an equal and opposite load on your pile head. Something gone weird with animation. In terms of different devices, effectively what you're doing is you are only creating a long duration load. That's all you're trying to achieve. So there are different ways to achieve this, and Statnamic has sort of gone a little bit by the wayside, I think because of the fuel problem. It's expensive, and then getting it across borders, shipping it was a problem. So a lot of people have moved to more cushioning type systems. So there's a couple of examples here from Japan. Probably move out of the way of the video. We've got basically a drop mass, as you can see, and they drop them on a series of springs that have been tuned to control the duration of the loading event. And you can see the differences in sizes here. So there's something down that's man portable, 200 kilonewtons, up to 2.5 meganewtons using a standard crane and some kind of rig to drop that on a cushioning unit. So you can get quite a variation of different system types and different approaches to it. Pseudo-static pile load tester, again, that's a drop mass onto springs. Here the springs are above and below the weight on the left-hand side. And then the dynamic guys tried to get in the action a bit. This is just a drop weight, and they dropped it onto what I call the egg box. So the egg box is just a deformable piece of steel that's coated in rubber. So when the mass drops on it, it traps air in the little egg box pockets, and that again acts as a cushion and deforms to try and create a longer load duration. Statnamic, we've just seen, this was the most common thing when I was doing my PhD, different rigs, 4 meganewton, used for lateral impact load simulations. They've used it before, so that isn't just sat on its side. It is about to load that pile as if it was a ship type impact. And you can see a range of different rigs there, right down to something that can go on a mini crawler and give you about 250 kilonewtons. I think the biggest statnamic test that's ever been done is 103 meganewtons. So there's quite a scope of size, different types of tests you can do and benefits to doing that. Oh, there it goes again. You didn't see it the first time. That's the same pile, just cycling, just reloading each time. You can quickly, not static testing, but you can do static different cycles at different pulse levels. And we might see that in some of the data in a bit.
That was a bit more impressive, wasn't it?
And I think the most modern evolution of this is what the rigs that Allnamics are using, based out of the Netherlands. And again, this just works on a drop mass system. We'll be able to see the video, and they use a series of recyclable rubber springs. So these are just rectangular, long cuboid type springs. They load them in. They've got different colored ones that can give you different duration of events. And again, they can control the height of the drop to control the magnitude of the event. And these guys supply all sorts of offshore monitoring as well. So they're using standard PDA type systems that they all supply themselves. So it's far less interesting because there's no fuel being involved. They just use hydraulics to pump that up to the height they need, and then they drop it and it catches as it goes. So it doesn't reload the pile. That's one of the problems with some of the early systems that people came up with, that you get a weight bouncing on the pile and then it's difficult to sort out what your load signal is, what your final displacement is, this kind of thing. I think also quite nice that it shows off what you can do in a congested site on working piles. So there's 3 piles next to them, or 4, quite very small compact rigs that you can get onto small sites and test as you go. So I think that's why I've used this example, the photo here of, you can see this congested site with lots of small piles where they're testing working piles, getting access to that, which is not something you might normally think about doing with a standard Kentledge or reaction pile static load testing regime. So there's much more scope for testing working piles, I think, with some of these systems. So that's my long list of benefits, obviously biased because I did my PhD on it, so quite happy to be pulled up later on it. Congested sites, we said, it's obviously fast, quick setup. You know, how long are you talking for a normal static pile? With reaction piles, maybe 6-7 days if you've got to get your piles in before you're doing anything. And then you could be up to 3 days, depending whether you're doing MLT or CRP type testing. Multiple cycles on a pile, as I've said. Can mobilize a pile. By that, I mean you can get some significant displacement into it. I've seen some dynamic pile tests, particularly in the north, in the Sleach, where they've said, oh, look, it's got great resistance and it's gone about 3 millimeters and it's got to peak, and then it strains, softens like mad. And they don't pick that up in a dynamic test. The good thing about statnamic and the rapid load testing methods is that you can get quite significant deformation in by varying your loads. So you can mobilize the pile and see if you are getting any work softening type behavior, which you don't always see with dynamic pile testing. Good for working piles, we've just seen that. Direct measurement of load, so there's no interpretation of that, it's just a load cell. Non-contact measurement of displacement. Very low chance of pile damage because you're holding that pile in compression during the event. That's part of the ethos of it. And hopefully more guidance and standardization. That's what I'm talking about today. large range of capacities, so you can do very, very big pile tests as well, and relatively safe. So you've got not stored energy that you might have in a static pile test if you're trying to put on a 50 meganewton test. If something goes wrong at 50 meganewton, you're going to know about it. Whereas with these methodologies, there's no stored energy. It's done in a different way. So as they get bigger, they become very cost effective, and they're much safer than some of the other techniques that you can use. So going a bit more towards drawbacks, being brutally honest, quite happy about that. That was what my PhD was on. When I started, a lot less experience and guidance, and that's something I've been trying to do a little bit about myself as an academic. Availability of equipment. Currently, I think you've got to go to mainland Europe, Holland, to get the nearest machines. So you're going to have to mobilize something that's going to cost you money. So you're going to have a relatively big job to probably get it onto Ireland, I think, to make it cost effective. Both dynamic and rapid load testing don't give you characteristic resistance directly. There's always going to be some analysis, not currently mentioned in EC7. Hopefully with the evolution they are, and the testing standards that we've created that are supposed to integrate with that. There are no model or partial factors in EC7. So how do you do design on that at the moment? And my area of interest is in clays, you're going to get big rate effects. So you're not pushing something at 0.01 mil per second, you're pushing something at a meter per second. And how do you deal with that in terms of rate effects? So I think just looking at the data here, you can see results of that cyclic stat dynamic test you saw on my site right at the start. We're putting different load pulses in. And as you can see, we're getting up to about the magnitude of the machine, which is 3 meganewtons on that cycle there. These are the same static test done afterwards on it. So a CRP is giving you about 2000, and a maintained load test is giving you about 1800. So that is your rate effect. That is your problem, in that it behaves differently. It's also interesting that we, even between two static pile tests there, we get very different results depending on whether they're drained or undrained or how they're behaving. So whatever we do, whatever kind of test, we've got to come back to characteristic resistance at some stage, and how do we do it? And maybe there's even a question there for static pile testing, because they are giving you different rate effects, different drainage regimes, partial drainage, undrained, viscous, who knows? And we all know the long one about, if we leave piles a long time, do they also change their capacity? So it does give you more of a philosophical question, what is our characteristic? But maybe that's a bit academic. And just to highlight down here, what I'm talking about with these rate effects, this is undrained, where we spend a lot of our time working. This is partially drained, so you can get massive rate effects just by testing too slowly, if that makes sense. So what is the right speed to test at? Probably there shouldn't be a standard speed. It should be probably soil dependent, but you can get much greater gains in pile capacity by going very slow. We work down here undrained. All my work is out here in the viscous regime, where the soil is moving very, very fast. So thinking about rate effects, I think, is an interesting thing anyway. Partial drainage, undrained, viscous, something that's useful to be aware of, I think. Being engineers and specifying things, we need precedent. We need to be confident in our methodologies, and the rapid load testing is relatively new. So before I started, there were 2 international conference proceedings on it, symposiums in Europe, and the regular stress wave conference. I think the next one's in Rotterdam soon. It's mentioned there quite a lot. There are European case study usages. So I'm responsible for one in Grimsby, which is the same as the Cowden Till. The Cowden Till, if you've heard about the Pisa testing, that's where they were testing the Pisa piles for monopiles. So it's been used for a long time by BRE, and Oxford ended up there doing for their Pisa monopile testing. So quite a bit of work there previously done by BRE, and then reported by myself and John Powell of Cone fame. In Holland, it's been used a lot. So there's a lot of documented studies, similar in the US. So the Kerr document there is like a BRE standard in Holland, and they've built up similar, and that's got databases for both Holland, Germany, and the US. So there's a lot more experience in Europe of these testing type methodologies. So those are just some of the probably documents. There is an ASTM standard already on it. Spewall, the ICE documentation mentioned it, because I helped write those bits in there. And then the Kerr guidance document is purely about rapid load testing. So there was already some sort of precedent, just not in the UK or Ireland. And then sort of where I came in, I got roped into being on a working group for TC341, where we got given the job of creating testing standards for dynamic load testing and rapid load testing. One of the problems we had, and if we're criticised, is that we had to develop those while there was no static standard. So the static standard came out actually after the rapid standards, because it started in about 2000 or before my PhD, and they still couldn't agree in Europe and come up with a standard. So I think it got cancelled about 3 times, that project, before they finally came up with a standard. Trevor will be able to tell us whether it's in EC7 with its evolution, because it's not currently mentioned, as I said, in the one we've got at the moment. And there are no model factors, which is a problem for rapid load testing. Why was I brought in? I think I've got a track record, even as an academic, of making things happen. There are several big publications with my name behind them, and I got brought in as the Yorkshire Terrier to try and bring it out. From Yorkshire, if you didn't know, and unfortunately our national dog is not as interesting as the Irish Wolfhound. I've got the Yorkshire Terrier, unfortunately. So when things seem to go wrong, I get brought in to make them work. So there were a lot of arguments. The working group had stalled. What I'll mention later is, as an academic, you see there's a lot of commercial interest. So maybe not in a Eurocode, but in a testing standard, everybody has a competing technology. So I was just battling all the time for things to go forward, but it was for commercial reasons, not technical reasons I was being held up. So what's in the standards and what's not in the standards, and what needs to be in the testing standards. So I'm talking particularly about the testing standards for the 2 types of pile testing we're looking at. This is just showing you some of the more of the work I did during my PhD and we brought on later in terms of rate effects. So here's the viscous rate effect on the left-hand side. And this just gives you a feel for what I was talking about, moving from. So these are static pile tests, but these are static pile tests done at very, very different speeds, if that makes sense. So they're constant rate of penetration tests. Standard rate in the UK was 0.01. These are model tests, and with servo hydraulics, I was able to get tests running at 500 mil per second, so half a meter per second. And here you can see the rate effect. So that's the problem. When you go faster, we're generating about 2.5 times capacity in clay. So clay has a massive rate effect potential when we go viscous. We then managed to do some very high-speed triaxial work much later, 2019, with one of my PhD students. And what he showed was that different clays also have very different rate effects. So we've got 3 different clays here. These are just rate effect indicators on the side. And he found that it changed with the gradient of the critical state line. So there's something fundamental that's controlling it. And when we looked back in the literature, David Muir-Wood showed that the surface area of the particles in clays affects their behavior quite significantly. So he found a link with slope of the critical state line, plasticity index. There's something more fundamental going on. So there's the problem of not every clay behaves the same, and they've got these very high rate effects, as I say. So me being a relatively simple beast, I came up with a simple equation based on both my lab work and the field testing that I came across. So all we do is we measure the statnomic resistance, take off the inertia of the pile due to its self-weight, and then we've got a little parameter here that is the rate effect that varies with velocity. And that actually comes out as something that Randolph and Simons created for dynamic pile testing. So it's got history as well. But me being simple, I just linked it with plasticity index. There's no point for me having loads of equations that nobody can find the parameters for, and you can't measure from a simple lab test. So all of my work correlates back to plasticity index, even though we use some very specialized machines to measure the rate effects as we went. So that's always my aim, to make it nice and simple, or nobody will ever use it. This is all going into an informative annex, was my aim. I never really got there, so it isn't in the informative annex. So in our standard, we've got a testing methodology, and at the end of it, because we needed some way of coming up with these rate effects, we thought we needed to have some design methods in it. So is the method any good? Tried it out in the UK, in London clay, in Cowden Till on the right-hand side. And I think my original stab at a method is this thing coming out here that seems to be doing quite a good job. BRE, we're into doing lots of different types of static tests, so none of those are quite standard. So it did quite a good job compared with some of the existing methodologies that people have tried to develop to analyze this in clays. And similarly in the Cowden till, this is zoomed in a lot more, and VRE doing tests at different speeds, which confused things a little bit. It did quite a good job. I think the important thing to note is that we've got 2 clays here in the UK. This is the rate effect parameter. So it's more than double in London clay than it is in Cowden till. So it's not straightforward that there is a one size 10% per log cycle that fits all. Rate effects aren't that simple. So we've got an informative annex. We need an analysis methodology in there. My method's not in there. So I get accused, or have been accused, of being an academic likes to shout about what he wants to do. Just blow your trumpet and get it in the standards. I was in charge of standard. My method's not in there. It is mentioned as something you might be able to use, but I'm also overly critical of everything I want to do and be perfect. It was only for one soil type. I thought there was a lot more going on. I think it's, I thought at the time it was a function of state and the strain level. So back analyze rapid load test on the top right there, back analyze test there for moisture content. So you're seeing an increase in rate effect with moisture content and very different strain level behavior during your test. And also, you know, we've got lots of different materials we're going to be testing in. So I wanted a method that will work in sand, clay, sleet, silt, whatever else. All my work was in clay. So actually it's mentioned, but it's not there. So I thought there was more work to do, typical academic. And there was more work to do, and we did it. So we built a very high speed triaxial rig. This can go about 200 millimeters per second. And my original guesstimate of what was going on was actually correct, as in we've got very different strain dependent behavior with rate effects. They only kick in at a certain point, they maximize and then they die away a bit. They're also very much moisture content or state dependent. So you can see very different rate effects for different soils. So none of this 10% per log cycle you get told, it's a load of rubbish. And also it varies with the moisture content. Not affected too much with over consolidation ratio or stress history. It seems to be affected more by state. So some of my early reasons for not putting it in were actually true, and we didn't work this out till after 2016. So in some ways happy with mine didn't go in. What we did end up though is we did end up with an informative annex that tells you what to do based on a methodology that came out of industry, based on a large database of different tests, and back down to a very simplistic methodology that anybody could use, because I like the simple methods. And all this does is takes off the inertia, and it uses something called the unloading point method. And basically all that means is it looks at the point where you've got zero velocity in the test, and it assumes that that is similar to your static power resistance minus the inertia because it's not moving. It worked all right, but it needed correction. So based on a database of a lot of tests, it came up with, or we came up with a corrected method. And this is one of the tables in here for picking for different soils to correct it. And not going into any great detail, also thought it was important that anybody and his Yorkshire Terrier or his dog could work out how to use the methods. So once you've got the data in the back of the document, it tells you how to use it step by step and even create all the graphs. So anybody could get the raw data from your pile testing person. If the dynamic load testing people tell you you've got to pay for it, just wave our testing standard in front of them. We got rid of that clause. So they have to provide their data for free. Some of the dynamic people try and charge for the real raw data. No, you have a right to have it, so don't let them charge you for it. But if you've got it, you can then feed it into this testing standard, and anybody should be able to get the same answer. It's not so specialized. So just coming to finish, hopefully close, last few slides. How then do I feel that EC7 should evolve based on what we've been doing in pile testing, and more generally, everything that's come out of the presentation. So there's the issue of lack of testing maybe going on. Can't speak for Irish ways you do things, but throughout Europe, I think there should be more going on, particularly when we're trying to be more efficient in our designs and reduce CO2 and concrete use, particularly trying to get away from conservatism. So I think they need to when they evolve, have awareness of our testing standards. So we've put a lot of work into making 3 standards that to do with piles. Hopefully they feed through and don't get ignored, because they were designed to feed into that document. So you've got a design standard, an evolved Eurocode 7, and then you've got these testing standards where you need to go to find out about particular different tests. Personally, don't treat them as the same thing. There's commercial reasons behind that I won't go into, but they are very, very different tests, as you'll be aware from our elephants, and also for people that have witnessed pile testing, and their analysis is very, very different. Rapid load testing is not dynamic load testing. It's a very different thing. It's not stress wave based, which that's where all of that comes from. They have their own testing standards now, as I said, so please evolve with those in mind if somebody can be bothered to sit down and read them. Should we attribute different model factors to different tests? What's our confidence in those different methodologies? Where do they come from? Personally, rapid load testing, no stress wave analysis, direct measurement of load. It is more of a direct measurement closer to static pile testing, but then I'm biased. So the dynamic guys will argue that they want better model factors than rapid load testing, maybe based on experience. But it does raise the question that's probably further down there. Where do the model factors come from that are determined in EC7? And maybe we can pull Trevor on that later, or maybe not. He might not want to answer that one. So, should you be giving less onerous factors for different methodologies? I think we should be doing more pile testing, as I said, and hopefully in an evolved EC7, it's encouraging that. Depend on risk. Do you know the site? Have you used the piling methodology before? I think piling testing, it's obvious to me, you do a design on a bit of paper and you come up with a pile resistance methodology, but there's nothing in there often on how we got it there or what kind of method we used. It's often based on some wished in place methodology. How does it correlate to real pile testing and real construction? And how then do you pick up when things go wrong? If you don't test piles, how do you know something hasn't gone wrong in the construction process? So I think there needs to be much more on what I call installation effects in our design methodologies as well, not just wished in place type design that we seem to default to quite a lot. So that's back to reduced factors, particularly if incentivizing testing. One thing I would be wary of if you specify rapid load tests and dynamic load tests, because of these rate effects and mobilizing the piles, you need to put a lot more load on, particularly the rapid load testing. You could see there we were putting nearly 1.5 times the load just to mobilize things. The rate effect is there, it isn't going away. If you come along and specify on these tests and you specify you're going to apply the static load test, it isn't going to do anything. It is a different beast and you need to think about what you're doing. But that I think then relates to getting contractors involved at an early stage. They know more about these methods than I do because they do it day in, day out. Why not get them involved and get the proper advice? Everybody can argue DLT and rapid load testing capture long-term behavior. I would argue that do static load tests capture the long-term behavior as well. We see a lot of these things that came out of Imperial about evolved pile capacity over long periods of time. So there's always an argument about, is it a static pile test? And I always argue, well, what is a static pile test and what is long-term pile behavior? So maybe don't get your knickers in a twist about it, and just any test is a good test. It's all helpful as far as I'm concerned. So I'm not involved with any of these organizations or methodologies anymore. More testing, better, horses for courses. If you've got a dynamic machine on site or a drop hammer on site, you're going to use DLT. It's obvious. You don't have to mobilize something. It's there. Use it. Any testing is good testing as far as I'm concerned. And then leveling one at Trevor, you might not want to, as I said, how are our model factors determined in EC7? I think it reminded me as an undergrad, I'm sure it was a Guinness beer map, but it might have been a John Smith. So sorry if I'm saying the wrong beer, but I was looking for beer maps and I couldn't find it. And it's 87.6% of all statistics are made up on the spot. So do our model factors come from statistics? And if they do, are they made up? I think they're confidence, but we can push Trevor on it when he's had a few beers. And then I just found out of interest, you might have come across William S. Gossett, who's supposedly one of the fathers of modern day statistics, and he came out of the Guinness Brewery. So he was trying to refine the actual process through using statistics. So I think it's quite funny. He's a bit like a code type working group member, I think I said. It says he's the concept of statistical significance, industrial quality control, which is what we're sort of doing, efficient design of experiments, and not least of all, consistently great tasting beer. And as I said there, I wish he'd been on my working group just for that reason, the last one. It just leaves me to say, obviously, thanks. As Carl says, and I'm on the second chair with booking this. We've been cancelling it and redoing it for a long time now. So I've been coming here for a long time. So thankfully managed to get in front of you by the end. So I'd just like to say thank you for Geotechnical Society of Ireland and Engineers Ireland for inviting me to do this. I'm very honoured to be Trevor's warm-up man. I think I owed him one. I lumbered him with the chairmanship of the ICE Geotechnical Engineering Journal after me, so I twisted his arm to do that. So he's getting one back on me here, but I don't mind. I'm also honoured to be associated with the name of Eamon Hanrahan and recognise his significant contribution to discipline and education in geomechanics. And thank you to all NAMICs for some of the slides and photographs and videos, etc. Thank you.
Thank you very much, Mike. Now I'm going to ask you to stay in front of the camera, and I'm going to. What we usually do at this event is that it's not moving on for me. What we usually do at this event is have the AGM afterwards, but because we've got a captive audience at this point, we usually do a little short piece on the chairman's report at this point. So I'm just going to tell you a little bit about what the society does. During COVID, the short answer is not very much. We've had a very quiet year. Next year is going to be, or the next season, 2022-23 is going to be a little bit busier. And the very first thing in that slightly busier year is we've got the society every 5 years hosts a large seminar in Portlaoise. That will be coming up in October of this year and will be on the topic of geotechnical engineering for renewable energy. Now we'll have about 12 speakers. We're not sure the exact number yet. We've got a lot of abstracts in. There'll be papers will be published afterwards. You will hear more about that, and it's one to keep an eye out for. It'll be a big event. It'll be nice to have people in a room together. A lot of people. We usually have around 100 people, so we're looking forward to that. We also have to choose the fourth Hanrahan Lecture. Now, the fourth Hanrahan Lecture should have been happening today, so you think we'd have made that decision by now, but that's something else we'll be looking at. That'll be in 2 years' time, but we have to give the potential speaker maybe not quite as much notice as Trevor's had, but certainly a reasonable amount. Two related things we are trying to do is put together a bit of a paper on raising standards in ground investigation in Ireland generally, and also to update the Irish version of specification and related documents for ground investigation in Ireland. Now, that's already published, it's out, but we're looking at a third revision of that. Now, Brian Byrne of IT Carlo is actually going to share a few slides. He's joining us remotely in a moment on that topic, so I won't say too much more about it. But a second aspect of that is we're getting a lot of feedback from non-geotechnical consultants that slimmed down versions, maybe even a user's guide rather than a sort of a shortened spec, would be really helpful to people. So that's something else we're looking at as an option, and Brian's going to talk about that in a moment. Our own constitution was sort of written for back when there was probably maybe only 20 people in geotechnics in Ireland generally, and I think we've gotten bigger. We've got over 100 people between in the room and joining remotely. So that's something else we've been trying to do for a few years, is just get the constitution of the AGM to reflect a bigger interest in geotechnics, and we haven't quite got that here. And the other thing we've been talking about for a while, and again got held up, is loads of lectures, including the ones today, have been given to the Geotechnical Society over the years, and we want to collect them all together, scan them, and publish them somewhere. So there are a few of the projects we're working at over next year. And I'm having fun again. There we go. But as I say, those two I wanted to highlight because Brian's going to talk to them in a moment. The Society is also Ireland's national representative on the International Society for Soil Mechanics and Geotechnical Engineering. Members of the Geotechnical Society can, if they choose, pay a €25 annual fee to also join the ISMGE. Kevin Flynn, our treasurer, is the person to get in touch with there. Basically, there's two ways of joining the society. One is just go to Engineers Ireland webpage and say you're interested, or you can fill out this form. Now, this form is useful because we do have members that aren't engineers. So there'd be particularly, members who are geologists or that are encouraged to join us. So we do have membership outside Engineers Ireland, and this form is a useful way for them to join. And if you were interested in joining the ISMGE as well, you can get this form. So say Kevin Flynn is the person to contact. I had his email up shortly, kevin.flynn@agl.ie. What do we do as part of ISMGE? Well, one of the things we do is we sponsor young geotechnical engineers to attend one of two conferences, either the European Young Geotechnical Engineers Conference or the International Young Geotechnical Engineers Conference. I think Trevor's probably going to discuss this a little bit more later. He's nodding, I think I'm right. He held a European conference here back in the mid to late 80s. And the money that raised has ever since provided the sponsorship for sending young engineers to one of these two conferences. Now, young is defined as under 35, which for a long time I felt was very generous, but no more. So the last conference, there was meant to be a conference in 2020 in Moscow, and we had selected Kevin Duffy to attend that. It got held up with COVID. Other events intervened. We genuinely do not know what is happening in Kevin Duffy and his trip to Moscow. He's still earmarked 3 years later. He's waiting even longer than Trevor's waiting, but they haven't said what they're doing instead. So we don't know. Last year was meant to be the year for the international conference, which was Australia. We decided that was too far away. Turns out we were a little bit lucky. It's actually going to be held in a couple of weeks' time. And then they haven't announced next year. So usually I would be telling you that towards the end of this year, young engineers who are interested in going forward to this should get in touch with Carlo, who's our third level liaison, and we would have an event here in November and would select somebody to go forward. As it happens, we don't know what's happening next year yet, so we don't know if that'll be happening, but keep an eye out, we might hear more. As I say, these conferences have all started getting bunched up a bit. So the Sydney conference that was meant to be last year will be happening shortly. At that as well, I'll be joining a committee meeting at that, where we'll get to vote on the new president who will be selected for 2022 to 26. It's preceded by the young engineers, they call it the 7th Young Engineers Conference. And then, as I say, the 28th one, where we did have somebody to go to. We don't know what's happening with it, but it's maybe coming up soon. Another thing, and a few people in the audience are involved in this, there's technical committees and various people with interests in certain topics join these, and these are the Irish representatives on the various ISMG technical committees. You'll notice Trevor's name on at least one. I think it's 2, is it? I'm moving on in case I forgot to put them in. So then the other topic that's important that we want to tell you about is RoGEP. So RoGEP is the Register of Ground Engineering Professionals. The Institution of Civil Engineers, the Institute of Materials, Minerals and Mining, and the Geological Society of London put this idea together to register initially, and our former chairman, Fintan Buckley, has been pushing very hard for the Institute of Geologists of Ireland and Engineers Ireland to be part of this as well. So there's now 5 organizations that can put people through. There's 5 different grades. Chartered engineers can go in for 3, professional specialist or advisor. In total, about 800 people are registered. Now, Fintan would usually give me the exact numbers, but he's off enjoying himself in Tampa and didn't have access to his computer. So he's listening in apparently, but if he's able to send us a text later, we might be able to get the exact number. But around 30 Irish people are registered. We are trying to push it up to about 50. We're getting there. And when we hit 50, we're hoping to approach Irish employer bodies to sort of publicize it further. I'm going the wrong way again. So usually there'd be 2 deadlines I'm telling you about for people who are interested. One of them is published, it's up on the Institution of Civil Engineers page 20th of July. They usually also have a deadline in October, but they haven't published it yet. All the documents you need to find that are there. It's very easy. Just go to ICE's webpage, and there's a link to registers, and you'll find the roadjet list pretty easily, or the roadjet documents pretty easily. So that's it for now. One other thing, as I said, Brian is going to join us shortly, so I'm going to ask Sinead to come back up and bring his slides on, and we'll make sure he can connect. We'll come.
Okay, can you see that now, Sinead?
Yeah.
Okay, so this should take about 5 or 7 minutes. If I bore you, I've done a bad job. If I don't annoy somebody, I've done a bad job. I'm hoping that we'll start some sort of a conversation.
Sorry, I'm just trying to look at the view of it here.
Yeah, it's moving on for me. There we go. Okay, so as Carl said, there's a number of reasons why we're updating the specification. There were some errors in the previous edition, although there's in 175 pages, there are going to be some errors. And then to update it to the current standards. And then the industry has moved on and there's been improvement. So they're really the 3 reasons. And we're looking for people to contribute, to give us suggestions with regard to changes that might be made also, particularly if you're using this on a regular basis, this document. Okay, so one of the things we started to talk about when we met, the 4 of us, we said, well, what is the quality of the specification in Ireland? And we didn't know. So I did this really, really intricate survey where I called the main GI contractors on a phone call, and I asked them a series of questions. And below now is some of the comments that they made. So their overriding view of the use of by engineers, civil, construction, structural, geotechnical engineers, one of frustration. There is a separation between the larger consultants and those who have in-house geotechnical engineers, and then the usually smaller civil structural engineering consultants. So how much, the next question then was, how much was the document used? For the larger consultants, it was used a lot. It's regularly used. It's often been modified to reflect the requirements. But for smaller civil engineering consultants, it's not used at all. And the phrases that were quoted to me very, very seldom, once I think, and what they do get is they get this cobbled together document. Now, these are not my words. And this is reflective of everybody that I spoke to. No one really had a different opinion. The documents that they get are not reflective of the actual project. There's a lot of some things that aren't relevant to the project, and there's missing things that should be in the project. So what ends up happening is the people who are trying to price the job are also trying to rewrite the specification. And their complaint is that they don't have time for that now. Like some of these people are trying to price somewhere between 12 and 20 jobs a day. So, and then when you do include things, like one quote to me was, the flavor of the day at the moment is frost heave. So people are including frost heave tests in their specifications, whether or not there is any requirement for them at all. And it makes the job expensive. Some of them have said for particular consultants, they don't have time to go through it to change the specification to reflect what they think the job should require. So as Carl said, one possible solution is for us to do a slimmed down document. Again, talking with the contractors, they reckon that our document is too big and it's actually scary. It's 175 pages, and a lot of civil engineers don't have the time, or they don't have the training to understand everything that's in it. And what they're looking for is this slimmed down document, maybe 10 to 20 pages long, that they can go through and they would use. So this is something that we're considering, along with updating our specification. And we were talking about, well, what might we do? What way is a simple document? What might be used for? And one of the things we thought, well, maybe we could use the GC1, GC2, GC3 categories. And again, just like Mike, if Trevor needs to slap my wrist, He can do that later, but it'll be virtual because I won't be there. So maybe the GCC1 is something that you know, civil engineers can price, because that's the majority of the jobs that are done in Ireland. And that might be what our document, our slimmed down document, reflects. So now I'm just about finished, but this is kind of a bugbear of mine. It's talking about accredited laboratory testing. Okay, if you want a blood sample taken for, you know, you think you might be sick, you want it sent to an accredited lab. Okay, if you're getting environmental samples done for your project, you want an accredited lab. If you want aggregates tested, you want an accredited lab. But for soil samples, it seems to be, well, not really. Why not? Because, well, it's expensive. Client isn't agreeable to it. There's a possible time delay to the project. And I'm just kind of reflecting on what happened 5 or 6 years ago before we started the all of the issues that came about with aggregate testing. And I'm just wondering, are we kind of creating something for ourselves where we don't require an accredited lab? This is what our specification says. So this has been in here since, I think, 2006. So this is part of our specification. So it's a standard that's produced by Engineers Ireland, and it reflects the fact that accredited labs should be used for soil testing. So if we want to do this, there's no cost to consulting engineers. There's no cost to contractors. And the contractor said they'll comply with and they'll use accredited labs if it's specified. And they told me this. So the reason that they're not providing accredited labs is because consulting engineers aren't asking for it. So if you think about your role as a designer, and I'm kind of, this is a bit of a stretch here, but a designer is responsible for quality assurance. Your design depends on particular information. And if you can't stand over your information, if it's not done by a competent lab, you don't know if it's done properly. Like if you look at what's been done to accredited a lab, like one of the things that's done is they send blind tests to different labs throughout the year, and they ask them to test samples. So 6 or 7 labs get what you would call the same sample, and they test them and they see what the standard deviation is, and you get you know, how well you do compared to other people. So I suppose what I'm trying to say is, in a way, specifying is designing. And there's no doubt about that in the construction regulations of 2013, specifying is designing. At the end of the day, then, who saves money? It's not the consulting engineers saves money, but who takes the responsibility? I would reckon it's the consulting engineers if something goes wrong. What we're trying to do with this specification, we're trying to make something good better. And hopefully we're trying to provide for the people who aren't equipped to use a 175-page document, but allow them to have a slimmed down version so that they can do work for the majority of their jobs. And hopefully also guide them into a place where they recognize where they're not comfortable and they're not qualified or equipped, they're not competent to take on a particular job. And then that's when they call in their geotechnical specialist. That is 6 minutes and I'm finished, and thank you for listening to me.
So we're returning now for Trevor's lecture. Trevor's lecture is the Hanrahan Lecture, and the Hanrahan Lecture was named after Professor Eamon Hanrahan. He was Professor of Geotechnics in UCD, well, of civil engineering in UCD for quite a long time. And a couple of the books he wrote for First for Borda, like, people still look at them, and my colleague recently found one in ESB's archives, which has only just returned to ESB after 2 years of COVID in my bookshelf. But you still look at them. There's one on peat and one on glacial seal that I certainly find to look at. As Fintan Buggy, a former chair of this society, that came up with the idea that we should have a biennial lecture. And it was quite an obvious choice that it should be named after Eamon Hanrahan. Now, Eamon's daughter, Maura, is here with us, Maura Hanrahan. She's going to just speak a couple of little words about her father, and then I will introduce Trevor.
Thank you very much, Carl. My father, Eamon Hanrahan, was a very pure scientist. He was a man who was greatly interested in the truth and in ideas. And this led to quite a lively time at our dinner table at home, where my mother and father had 5 children, and most dinner times were spent in pursuit of somebody's version of some truth. He was a pure scientist, but he was also very applied. He was always trying to find ingenious new ways of doing things, more creative ways of doing things. This was not always helpful. I do remember the rasp in my own voice on a few occasions when he would be trying to give me advice about say if I was cooking, and I would say, Dad, would you please just back off? I'm going to follow the recipe here. I don't need new ideas. But his attention, I think, to new ideas was part of his belief that research was an evolving thing. And as we heard from Mike was saying that this afternoon as well, all research, if it's creative, evolves, is built upon, and is often superseded. And in that spirit, I recall an occasion when we took my parents on holidays with us quite a lot, my husband Tony and our 2 children, and we went several places on holidays. But one year we were down in the south of France in Provence, and we went to see this extraordinary Roman aqueduct, the Pont du Gard, that I was dumbstruck. I think we were all dumbstruck. My father had never seen it and said he would love to see it. And he spent ages looking at it and walking around it and photographing it and so on. And he was suitably impressed, but he just couldn't resist saying on the car on the way home, now, of course, you know, Maura, he said, we could do all that now with 1 2-inch pipe, which engineers among you may understand. So it is true, I think, that research gets superseded and gets built upon, but there are some things that really last. And these lectures are a great honor to us in our family. I was in Switzerland for the last few months with my first spell of duty and enchantment with my first grandchild, who was Eamon's first great-grandchild. And last week when Carl was talking to me about, when we were in communication about the letter, you know, the way you walk around a house with a new baby, and the child is now 10 weeks. And I was saying to him, I was sort of trying to whisper to him that this lecture was taking place and that it was a great honor for all of us and that we would tell him about it more in the years to come. So we are very grateful to the Geotechnical Society for this honor, for our father, and very grateful this year for Mike and Trevor, and indeed for Carl, and for you all for your attention. So thank you very much.
Thank you very much, Maura, and congratulations on coming here, grandparent as well. So Trevors will be coming up now shortly. I think maybe it might be a good idea if I was to just thank our sponsors at this point as well, which I know it's very grubby, but you know, they've helped. So we've 2 committee members who both work in site investigations contractors. So Ground Investigations Ireland Limited is one of our sponsors, and IGSL is another sponsor. Connor is here with us today. Paul is joining us remotely. Irish Tar provide materials, and also Screwpile. Donald from Screwpile works closely with our treasurer, and they're based near Fermoy, so they're our 4th sponsor. So Trevor has been in Trinity since 1977, and around that time he founded this society as well, the Geotechnical Society. Prior to joining Trinity, he had already received his civil engineering degree there in 1971, and then a PhD from Cambridge. He also worked for Sir William Halcrow and Partners for a few years in between. His involvement in Eurocode, and I presume it wasn't called Eurocode 7 back there, it was back in 1981 when he joined as an Irish member of the committee that prepared the model code for Eurocode. To this day, he's still in 3 task groups who are working on the next 3rd edition of it. In addition to that, he was also the secretary in 1987 when Dublin held the European Conference on Soil Mechanics and Geotechnical Engineering. The trust fund, as I mentioned earlier, that came out of that sponsors young engineers to go to young engineers conferences to this day. He was also editor, as was Mike earlier, of the IC proceedings on geotechnical engineering. That was between 2012 and 2016. He's a fellow of the ICE and he's also a fellow of this institution, the Institute of Engineers of Ireland. Something that happened about a year and a half ago as well, with his involvement on Eurocode, he was given an award by NSAI for services to EN 1997. The award is called the 1997 award. It sounds like, you know, it was invented for him. It isn't. Ken Murphy of NSAI is here. It was the year NSAI was founded, so they've named the award after him. I think it's kind of amusing that he, the code he's working on, it's such a similar name to the award he was given, but that's just coincidence. So that award was given remotely. I think maybe it might be a nice idea to give him a little round of applause for that now. And with that, I'll invite Trevor up to present the 3rd Hanrahan Lecture.
Well, Carl, thank you very much for that kind introduction. I'd like to also thank all the people for coming to the lecture this afternoon, and also those people who are online. Hopefully, I think there are a number of people abroad who are online. I told them about it and they said they would join us. So welcome to them and thank you for joining the lecture. Also thanks to Maura and Tony Hanrahan for your lovely introduction there about Professor Hanrahan, and for joining us too as well at this session. I'm starting with a few acknowledgements. I should put my glasses on actually first, if I can find them. Oops. As usual, they're in the last pocket I look in. So, as you've been aware, this lecture should have taken place 2 years ago. So after, I'd wish to acknowledge and thank the committee of the Geotechnical Society for the honour in inviting me to present this 3rd Hanrahan Lecture. Kieran Riley, the previous chair, who issued the original invitation, and then Carl Brangan, who organised so many reschedulings. This is the 5th date, in fact, we've had for the meeting for today's event. Ken Murphy, who's here present from NSAI, Eric Farrell and Kieran Riley for comments on drafts of this presentation and providing me with information and photographs, which I've used. Many geotechnical friends and colleagues in Ireland and Europe who have shared their knowledge of geotechnics and for their friendships. And then I better not forget my wife and Diane and family for their support and patience, putting up with me working on my presentation, often late into the evening or night, and not being available to look after grandchildren when I think Dan thinks I should have been. So the question topic I've chosen is how geotechnical design in Ireland and the rest of Europe has advanced with Eurocode 7. So I'm going to have this plan for the lecture. First of all, looking at the situation prior to Eurocode 7, then the start of Eurocode 7, then some challenges in drafting it, then Eurocode 7 and how it relates to the various standards bodies, the regulatory background and Irish standards, spread foundation design example, then the 2nd generation of Eurocode 7, and finishing up then with some conclusions. Now, the situation prior to Eurocode 7. When work started on Eurocode 7, it was in 1981, there was no Irish standards for geotechnical design. Ireland didn't have a dedicated national standards body. In Ireland, responsibility for standards functions in construction was shared by a number of organisations, including the Institute for Industrial Research and Standards, IIRS, and First Fervitha, and a few others as well. Geotechnical design in Ireland was generally carried out in accordance with British codes of practice or standards, with separate codes for different geotechnical structures. For example, you had CP2, Code of Practice for Earth Retaining Structures, issued by the Institution of Structural Engineers, and that was published in 1951, and CP 2004, Code of Practice for Foundations, which was published by the British Standards Institution in 1972. And in Europe then, most countries had their own different standards for geotechnical designs, reflecting national practice and their ground conditions as well. So that was it prior to Eurocode 7. Now, if we look at CP 2004, it provided much advice on the design and construction of spread and pile foundations and caissons. And that's a photo there of the cover of the volume, a green volume there, Code of Practice for Foundations. This and other codes of practice provided no requirements, only recommendations, since the operative verb used in these was should, not shall. It was based on the allowable bearing pressures with global factors of safety. There was very little guidance provided on the safety level required, and no advice provided on the selection of ground parameter values. It stated for cohesive soils, it's always necessary to ensure that the foundation is safe against shear failure by taking presumed bearing value not greater than the ultimate bearing capacity divided by a suitable factor of safety, conventionally the order of 2 or 3. And then with regard to non-cohesive soils, it said the factor or cohesionless, the factor of safety, no factors of safety were given in the case of cohesionless soils. There's not a great deal of guidance there on the level of safety. Now, Irish guidance design document. For guidance on the properties of Irish till soils, as Carl has mentioned, many engineers use Professor Hanrahan's booklet, Irish Glacial Till, Origin and Characteristics, published by First Fervitha in 1979. Obviously, it's still been used, according to Carl there. It was certainly used back then. And that's a copy of it. It's looking a bit worn at this stage. That's the cover of the booklet. And that's the inside page of it, the title page. And you can see there, maybe on the bottom, Professor Hanrahan's name, E.T. Hanrahan, as the editor of it, or the author of it. Now, bylaws. The only regulations relating to geotechnical works in Ireland prior to 1981 were the bylaws of the corporations of Dublin, Cork, and Dún Laoghaire. And that's a copy of the bylaws of Dublin. And they were published in 1949. They were still being used in 1981. And then when it comes to Dún Laoghaire, those are the bylaws for Dún Laoghaire. They were published in 1959. The bylaws requirements for foundations, both texts, the texts in both were almost identical. The only difference was that the Dublin bylaws referred to different people compared to the corporation bylaws. So I'll come to that at the bottom. Regarding foundations, both bylaws stated that clause 12, that every foundation shall rest on suitable ground and shall be constructed to sustain and transmit safely all loading imposed thereon. However, there's no definition of what suitable ground was or what to transmit safely all the loading imposed meant. Verification of this requirement was through inspection from the local authority. And clause 109 in both documents stated, every person who shall proceed to execute any work to which the bylaws apply shall, before proceeding to fill any foundation, give the city architect or building surveyor, in the case of Dublin, or the borough surveyor, in the case of Dún Laoghaire, at least 2 clear days' notice in writing. I'm sure today, 2 days' notice wouldn't be sufficient. Now, let's look at the IEI and the ISS MFE. Up to 1977, there was no professional organization specifically for geotechnical engineers in Ireland. And this relates back to what Carl was mentioning at the start of in his talk on the GSI. So in 1977, Matt O'Donovan, who was the Secretary of the Institution of Engineers of Ireland at that time, noted that contrary to the general trend throughout the world, the membership of the Irish National Society of the International Society was falling, the ISS MFE. So the Irish National Society was not active, but the IEI paid the annual subscription to the Irish Society. So Matt was looking for a way of finding someone to cover those costs. So in November 1977, to reverse the falling membership trend, Matt O'Donovan called a meeting of geotechnical engineers, which was held at the IEI with a view to the formation of an Irish Geotechnical Society. So that was November 1977. Then at this meeting, it was attended by Professor Hanrahan from UCD, Professor Kerwin from TCD, who was the soil mechanics professor there, and a number of geotechnical engineers from practice and academia. I think some are here this evening. And at a subsequent meeting then in December 1977, just a month later, it was agreed to establish the Geotechnical Society of Ireland as a society within the IEI and for it to be the Irish member society of the ISS MFE. The work to form the Geotechnical Society was carried out in 1978, and Professors Hanrahan and Kerwin at that stage decided not to become involved in the new society, but they left it to younger engineers. A committee was established for the GSI with Frank Motherway. I think he's watching online. I was hoping he would attend, but I think he's now got thinks he might be COVID connection from the IRS as chairman, and Eric Farrell, who is here with us, was appointed secretary. And the statutes and membership rules for the new society were agreed and allowed people involved in geotechnics, but not members of the IEI, to become members of the GSI, as Carl has shown us earlier about joining the members, joining the IEI, joining the GSI, still the same rule applies. And then a program of lectures was established and was presented in 1978. I think there was 2 sessions in that year. Political situation now prior to Eurocode 7. Politically, in 1981, Europe was divided into 2 zones, East and West, with the Iron Curtain and very little communication and great restrictions on travel between the 2 zones. In the West, in 1973, Ireland, the UK and Denmark joined Belgium, France, West Germany, Italy, Luxembourg, and the Netherlands to become members of the European Economic Community, EEC, also known as the Common Market, which is the precursor to the European Union. And Greece then joined the EEC in 1981. And up to 1977, there was a one-to-one link between the Irish pound and the pound sterling. And this link with sterling was broken in 1977 when Ireland joined the European Monetary System, the EMS, but Ireland did not. So those are the countries then that were involved in the EEC at that time. You see, they are very much the Western fringe of Europe with the Iron Curtain coming down there. So that's the map showing the EEC countries in 1981. Now let's look at the start of Eurocode 7. In 1974, a number of European universities and representatives of the engineering profession decided to prepare harmonized European standards for structural design based on the limit state design method. Then in 1975, the Commission decided on an action program in the field of construction based on the Treaty of Rome, with the objective being the elimination of technical obstacles to trade and the harmonization of technical specifications. And within this action program, the Commission established the Eurocodes, a set of harmonized technical rules for the design of construction works, which would initially serve as an alternative to the national rules and ultimately would replace them. The European Commission decided to link up with and support the work that had already begun on the preparation of harmonized European standards, so that from the start, the Eurocodes were based on the limit state design method. Now, the plan for Eurocode 7 and the Irish connection to it. In 1980, the Committee of the European Commission responsible for the Eurocodes was planning to draft Eurocode 7 for geotechnical design, but unlike for the other codes, there was no model limit state code to start from. Professor Kevin Nash, Secretary General of the ISS MFE and Professor at King's College London, and also a graduate of Trinity College with Irish roots, wrote to the Eurocode Committee saying that the ISS MFE was keenly interested in drafting a model code for Eurocode 7 and reviewing geotechnical design practice in Europe. He stated the ISS MFE considered it is important that Eurocode 7 is established as a flexible code in order to take the large differences in the physical environments within the area of the community into account, and also to allow for future scientific development of foundation engineering in Europe. I think this relates back to what Mike Brown said in his lecture earlier about the code needing to be flexible. And hopefully that has been achieved in what has been published, and certainly to allow for future scientific developments is important. So in writing this statement, he was correctly anticipating some of the challenges that would arise in the development of Eurocode 7 and the eventual form of Eurocode 7. Now let's look at the start of Eurocode 7. The Commission accepted the offer from Professor Nash to establish the ISS-MFE committee to prepare a model code for Eurocode 7. And hence, in 1980, Professor Nash wrote to the National Geotechnical Societies of the 9 member states plus Greece. Actually, I think he only wrote to the 8 because Luxembourg doesn't have a national society, which was due to join in 1981, inviting them to nominate a representative to the ISS-MFE committee to prepare a model code for Eurocode 7. The GSI committee received this letter, and Trevor, myself, then was appointed to be the Irish representative. So this means that there's a link between Professor Nash and this lecture today. I wouldn't be up here today, I think, but for Professor Nash having written to the GSI looking for a nomination and setting up the Eurocode committee. But there's another link. 3 weeks ago, I was in London for the Hanrahan Lecture. And there's a link between Professor Nash and the Hanrahan Lecture this year as well. The Hanrahan Lecture this year was given by Professor Stefan Trevors, and he was talking on the unexpected and unusual in geotechnical design or geotechnics. And in his case, the unusual, well, one of the things he was mentioning was obviously the COVID. His lecture was also postponed for 2 years. But his lecture was very unusual in the fact that it was due with chemical effects in ground engineering. He was interviewed by Professor Nash because he did his first degree in natural sciences and chemical engineering. So Professor Nash took a risk. He invited him for an interview and took him on as a research student to investigate chemical effects in grout in retaining walls, grout for retaining walls. And since then, he's done a lot in trying to understand the chemical effects that happen in geotechnical engineering. So that was his lecture today, our lecture 3 weeks ago to the Hanrahan Lecture. So that linked back to Professor Nash, just like I think this one can be linked back to Professor Nash. So I thought that was an interesting coincidence. Professor Niels Krebs-Oversen from Denmark was appointed chair of this Eurocode 7 committee. And at that time, Denmark was the only common market country with a limit state geotechnical design code. So there's very little experience in Europe of limit state design and geotechnics. Now, the first working meeting of the Model Code Committee was held in Paris in May 1981, with subsequent meetings held in different EC member countries. And Professor Nash died suddenly, aged 59, in April 81. In 1982, a new president of the ISS-MFE, Professor Victor de Mello, decided it was not appropriate for the ISS-MFE to be involved in standard preparation. Hence, he withdrew the ISS-MFE support for the Eurocode 7 committee, which therefore became an ad hoc committee. So we were really kicked out of the ISS-MFE at that stage. There was no EU or national funding for members to attend meetings. Hence, the GSI had to raise funds from consultants and contractors to support the Irish representatives' attendance at the Eurocode meetings. And certainly we were very grateful for the funding I received. I was very grateful for that. Now, when meetings were held in different countries, as well as working on the draft of the model code, local examples of geotechnical interest were visited. And that's a view of us having a meeting there. I think it was in Brussels. I won't try and pick out many of the people there. I think I haven't really got time with this, but one thing I will mention, if you look at the people there, we've all got lots of papers in front of us. It was before laptops. And we exchanged our drafts through the post. So it was a very different to today, very different. And everything's done online. And when a lot of the documents we're sharing are up on the web. So we're all editing the same document. And so we can see what each other's edits are. So it's very, very different nowadays. Much easier now doing it online. That was Brian Simpson there with his finger in a crack in a house in Seville, where where there was heave of the soil due to expansive soil. He was building due to expansive soil. That's a leaning church tower in Delft on soft ground. A lot of the meetings were held in Delft, because Delft is a good central place we found, and very strong geotechnical group in Delft. And we also have some social aspects to the visits. And we went on a cruise in my wife tells me it was 1984, because it's just before one of my daughters was born, the fourth one, and the third one. And it was the canal cut through the rock. So I think that should be 1984. Now, Eurocode meeting in Dublin. That's on the cover slide to this lecture. That's the Eurocode meeting in Dublin, the committee meeting there. And you see the representatives from Belgium, Denmark, France, Germany, Greece, Ireland, Italy, and Netherlands. There's no one from Luxembourg, so there are 8 countries being represented there. And then the daughter or the granddaughter of this man here, the chairman, the secretary, Wim Heinen from Netherlands, she drew the cartoon of the people at the meeting. And I don't know if you can make out the flags, that each one's carrying a flag. I'm carrying the Irish flag there, so that's me. The man here up with the question mark over him, he's not in this photograph, but he was the committee. There's been 2 photographs taken. He was from the commission, and he was there to monitor that we were behaving ourselves and working correctly. But the person who took that photograph is present in this photograph. It in fact is Eric Farrell, who's there, and he took that photograph from which the cartoon was made. So Eurocode acceptance by the ISS MGE. The Model Code Committee was completed their work in 1987 and submitted a code to the EC. The EU then agreed to sponsor work on the preparation of the ENV, or a trial version of Eurocode 7. Professor Bengt Broms became president of the ISS MFE from 1985 to 1989. And he's a European, he was from Sweden. And maybe he was more favorable to Eurocode for that reason, because the previous man was from Brazil, Professor Victor de Mello. But anyway, whatever it was, under his presidency, one thing happened. The ISS MFE changed to the ISS MGE. So the F was for foundation engineering and became geotechnical engineering, so it made it broader, much more inclusive of the different aspects that were covered by the committee and of the society. And then, in addition, it was considered appropriate that the ISS MGE should become involved in the development of standards. The first conference with sessions on design codes was held at the International Conference in Rio de Janeiro in 1989. And since then, the ISS MGE has been actively supporting the development of codes for geotechnical design, established committees. For example, there's been ERTC 10, evaluation of Eurocode 7, and one which was on the screen that Carl showed earlier, TC 205, safety and serviceability in geotechnical design. Now, European Conference, Carl mentioned that as well. Largely as a result of contacts established in Europe through the involvement of Eurocode 7, the Geotechnical Society of Ireland put in a successful bid to host the 9th European Conference of the ISS MFE. It was held in Trinity and the National Concert Hall on the 2nd to the 5th of September 1987. And that was 10 years after the formation of the GSI. And the organizing committee consisted of Bill Quinn, who's here, Eric Farrell, also here, myself, John Higgins, Martin Grace, and Tom Widdis. So 6 of us, we organized it. It turned out to be a very successful conference. There were 491 delegates and 150 accompanying persons, and it made a sizable profit. And part of the profit, as Carl mentioned as well, was used to establish a geotechnical trust fund that for many years funded geotechnical research at Irish universities before state funding became available. And most geotechnical engineers in Irish universities today received awards from the Geotechnical Trust Fund for their PhD research. And as Carl mentioned, the fund was also used early on to fund people to attend the Young Geotechnical Engineers conferences. Now, the conference theme, the theme chosen for that conference was groundwater effects in geotechnical engineering. And that's the cover of the proceedings. You probably can't see the detail on that, but the authors of the proceedings there, the first one there is Professor Hanrahan. So the theme was timely because how to handle groundwater effects is one of the challenges posed for those drafting Eurocode 7. And Professor Hanrahan was one of the editors of the proceedings volume. He also presented one of the 3 invited special lectures, which was entitled Drainage, Groundwater Lowering, and Consolidation. Another special lecture was the Nash Lecture, named in honor of Professor Nash again, presented by Professor Berland on the teaching of soil mechanics, a personal view. And this has been a very influential paper, and it's been frequently referenced, particularly by people in academia. So it's been a very, very influential paper presented at that conference. Now, let's look at the challenges in drafting Eurocode 7. Eurocodes were conceived as a harmonized set of standards for the design of structures using different materials. Separate codes were prepared for design using different materials, whether concrete, steel, timber, masonry, and soil or rock. And a head Eurocode was prepared with the general design rules to be adopted by the harmonized Eurocode for each material. And a separate Eurocode was prepared for the loads, which are called actions in the Eurocodes, acting on structures. The design philosophy adopted was the limit state design method, as I mentioned earlier, with partial factors applied to resist representative actions and characteristic material properties. And designs 2 Eurocodes aim to achieve structures with a particular target level of reliability. In other words, an acceptably low probability of failure. So there is a target to aim here in these, which really wasn't in the previous codes of practice. Now, the main difference between geotechnical and structural design, the components are the same. However, while Eurocodes are harmonized set of standards for structural and geotechnical design differs from structural design due to the following features of soil, which have presented challenges for those drafting Eurocode 7. First of all, it's a natural material. All the other ones are manufactured. So they're manufactured to specification. This soil is natural. It's particulate. So that means it's a frictional material. It's 2 or 3 phases. In other words, it includes soil particles, water, and air. It has a wide range of particle sizes, and this leads to time-dependent behavior. It's inherently variable. It's also spatially variable. It's ductile. It's dilatant. It's compressible with a low shear stiffness, or some has a low shear stiffness, and nonlinear and complex stress strain behavior. So those are the challenges that are the features that had to be proposed to challenge. So let's look at them individually. Soil features and the consequence and implications for Eurocode 7. Being a natural material, soil property values must be determined, and that's part of the design process, rather than being specified as for manufactured. So therefore, Eurocode 7 has 2 parts. We've got part 1, general rules for geotechnical design, and part 2, geotechnical investigation and testing, requirements for those. Since it's particulate, it's frictional behavior, so strength depends on normal stress. Therefore, you need care factoring loads, as they're unfavorable when acting as loads, but they're favorable when contributing to the resistance. So you need to be very careful how you factor them. And 2 or 3 phase materials. Soil behavior is a function of the effective stress, since the mineral particles have shear strength, while the water and air have no shear strength. So therefore, the principal effective stress needs to be taken into account. 2 additional limit states relating to hydrostatic and seepage groundwater pressures also were required for Eurocode 7. Then the wide range of particle sizes. The wide range of particle sizes causes a wide range of permeability. So dissipation of pore pressure may take a long or short time, hence the need to consider both undrained and drained conditions. It's inherently variable. And the inherent variability of soil properties is usually much greater than the variability of permanent loads. Hence, the partial factors on loads in Eurocode 7 are usually much smaller than those in structural design, and the partial factors, for example, the partial factors on permanent variable actions in Eurocode 7, taking design approach 1, combination 2, are 1 and 1.3, compared to 1.35 and 1.5 for structural design. And then larger partial factors are generally chosen for ground properties. For example, 1.25 on tan-phi compared to 1.15 on soil strength, on steel strength. And then spatial variability. Well, since soil varies spatially and the volume of soil involved in any design situation is much larger than the volume of soil tested, it's not normally appropriate to select the 5% fractile of test results as the characteristic value. Therefore, a special definition was required for the characteristic value of a soil property. So the definition then given in Eurocode 7 is that the characteristic value of a geotechnical parameter should be selected as a cautious estimate of the value affecting the occurrence of the limit state. And each of those words is important. It's a value that has to be selected. So you have to take a definite choice and make considered choice on when you're selecting it. It's a cautious value, and it's an estimate, and it's the value affecting the occurrence of the limit state. So those four words are all important when you come to select the characteristic value. Now geotechnical engineers have a definition for the value of the soil parameter to be chosen for use in geotechnical designs and have a value to aim for. And this was an important and innovative development because prior to this definition in Eurocode 7, the value of a geotechnical parameter for use in design calculations had not been defined. Engineers had to use their judgment and experience with no guidance. Often geotechnical parameters used were the values provided by ground investigation without any consideration of the design situation or the relevant limit state. Now go back to the ground properties again. The seventh one was ductility or ductile. Soil can undergo very large deformation before failure and still retain significant shear strength. And this ductile nature is beneficial because when soil supports a redundant structure, areas that are more heavily loaded or weaker areas of soil will yield, allowing load to be transferred away from those areas to the less heavily loaded or stronger areas. And this allows partial factors on loads in Eurocode 7 to be less than in structural design. And dilatancy. Coarse soils dilate and expand when sheared, exhibiting a peak friction angle phi peak, which falls to a critical state or constant volume angle when the soil is sufficiently sheared. It's important to consider the strain at failure and strength available to prevent failure. Eurocode 7 states that the strength parameters values, whether peak, critical state, or residual, shall be interpreted appropriately for the limit state considered. So you need to consider which are the appropriate values for your limit state. Then compressible, soil is normally much more compressible and less stiff than structural materials, and it can undergo large deformations exceeding the limiting values. So the controlling criterion then is often limiting the deformations rather than preventing failure. And geotechnical designs are therefore often controlled by serviceability considerations rather than ultimate limit state requirements. And number 10, nonlinear and complex stress strain behavior. It's difficult often to determine appropriate parameters and to model soil deformations, so it can be difficult to predict deformations reliably. For some geotechnical design situations, ultimate limit state calculations may be carried out with appropriate partial factors to limit the mobilized shear strength, and hence to limit ground deformations as well as to prevent failure. So moving on then to the next section, which is standard bodies and the benefits of Eurocodes. As the work on the Eurocodes increased, with more Eurocode parts being prepared, and as the number of countries in the EU increased, it became clear that the Commission, which was a civil service type of organization, was not the appropriate organization to be developing and publishing codes of practice for engineering design. This problem was reflected by the slow progress on the Eurocodes since the Commission became involved in 1975, and the difficulties in obtaining agreement on the format and how they related to existing European and international standards. Hence, in 1989, the Commission decided to transfer all the work on the Eurocodes to a standards organization. But to which one? Well, there are two main ones. The first one is ISO, standards organization known today as ISO. It began in 1926 as the International Federation of National Standardizing Associations. I seem to have lost the top of my screen there. Have you got it? No. The organization focused heavily on mechanical engineering. It was disbanded in 1942 during the Second World War, and the initial meeting to reorganize it under its current name, ISO, or the International Organization for Standardization, occurred in 1946 in London, when 65 delegates from 25 countries met to discuss the future of international standardization. And there they are. It's a very different photograph, I think, to what if you got a group of people today, how they would look. They think it must have been a very cold period, all the heavy overcoats and looking very glum. It was only shortly after the Second World War. ISO is an independent, non-governmental international organization, and its name, it's not an acronym. So it doesn't stand for International Standards Organization. It's not, or initialism, but it's the same name in all languages. ISO is derived from the Greek word isos, meaning equal. So prior to 1981, ISO had started to draft a standard for geotechnical design. However, by 1981, this work had not been completed and had stalled, as I mentioned earlier. ISO being an organization with membership of 165 national standard bodies throughout the world, including Europe, it was not considered suitable to be responsible for drafting European standards. Standards also published by ISO are voluntary, not mandatory for ISO members to adopt. And for these reasons, the European Commission decided to transfer the work of preparing and publishing the Eurocodes to CEN, the Comité Européen de Normalisation, or the European Committee for Standardization. And CEN was founded in 1961, and CEN took over responsibility for the Eurocodes on the 1st of January, 1990. It was logical for the Eurocode work to be transferred to CEN because the mission of CEN is to foster the economy of the EU in global trading, the welfare of European citizens, and the environment by providing an efficient infrastructure to interested parties for the development, maintenance, and distribution of coherent sets of standards and specifications. So that's the mission of CEN. The move to CEN occurred soon after the collapse of the Soviet regimes in Eastern Europe, resulting in the removal of the Iron Curtain in 1989 and the reunification of Germany in 1990. An important consequence then of the move to CEN has been the involvement of all the CEN member countries, some of which are not members of the EU, and some of which were formerly communist states in the eastern zone of Europe in the development of Eurocode 7. CEN now has 34 national members working together to develop European standards, called ENs, in various sectors to build a European internal market for goods and services and to position Europe in the global economy. The 34 national members of the standardization bodies of the 27 European member states, the 3 European Free Trade Association countries, EFTA, plus the Republic of North Macedonia, Serbia, Turkey, and the UK. So that's a map of them. So you see the dark blue there. There's a lot of all the countries nearly in Europe are members. So the 34 blue states, fingers crossed. Yep. So the blue member states, 27 EU countries, North Macedonia, Serbia, Turkey, and UK. See, and then the EFTA countries, Iceland, Norway, and Switzerland in the north, and 16 affiliates, purple. You'll see the former Yugoslav countries, the 3 or 4 of them there are affiliates. And also Belarus is an affiliate, interesting too, and Ukraine is an affiliate. Also Georgia and the countries down in that part of the world. And some North African countries are affiliates too. So you don't have to be European, it appears to be an affiliate. CEN's working on preparing standards carried out by technical committees. 250 was established in 1990 to oversee the development of the Eurocodes, with subcommittee SCs for each Eurocode. The British Standards Institution holds a secretariat for TC 250 and has been able to do so because of the UK standards body. It's remained a SEN member, even though the UK has left the EU on the 31st of January 2020. Subcommittee SC7 of TC 250 is responsible for Eurocode 7, and it's hosted by the Dutch standards body, which is NEN. Over the years, SC7 has set up many working groups, task groups, evolution groups, and project teams to prepare and review and revise Eurocode 7. And these have involved mostly voluntary input from a very large number of geotechnical engineers, from consultants, contractors, research organizations, and academia. And many Irish geotechnical engineers have been involved in these SC7 activities. That's a photo of a meeting, participants at the SC7 working group meeting at the Dutch Standards Institution office in Delft, 2019. It's the last face-to-face meeting of Eurocode people, I think. So that's over 2 years ago. Since then, all the Eurocode meetings, they've been held online. And certainly with all the working groups, it would have been impossible to make them face-to-face. So working online, in fact, has been very necessary and very productive in the 2 years since that meeting there. Just to point to a few people, Adriaan van Setters is the SC chair. Paul Morrison, who I think might be tuned in. Welcome for all of you are. He's a director of Arabs, and he's heavily involved in the working groups at the moment. He's on one of the design groups. And then Andrew Bond up on the top balcony there. He was the past chair of SC7, and then I don't know if anyone's seen where I am, but that's me there on that place there. So moving on, once SEN took over the management of the Eurocodes in 1990, they progressed much more rapidly. The trial version of Part 1, General Rules, was published in 1994 with a design method involving 3 cases, A, B, and C, and partial material factors. There then followed a trial period during which there was considerable debate among the geotechnical communities in the SEN countries. It became clear that while much of the text was acceptable, some countries were not happy and sought the inclusion of partial resistance factors as well as partial material factors. The EN version was then prepared and included 3 design approaches that allowed the use of partial resistance factors as well as partial material factors. So it moved from the cases to design approaches. And the standard version of Eurocode 7, it received a unanimous vote of acceptance by the SEN members bodies in 2004. It was critical to receive a unanimous vote in 2004 as Eurocode 7 Part 1 in order to ensure the new code's success and acceptance by the construction industry as an EN standard throughout Europe. Once a standard is published by SEN as an EN, all the members must adopt it as their national standard, with a national annex giving the partial factor values to be used in their countries and withdraw any competing national standards. Eurocode 7 is published by SEN as an EN, and so the same standard is now used for geotechnical design in all the member countries. In contrast, standards published by ISO are not mandatory unless they are adopted by SEN and published as EN ISO standards. So if they are published as EN ISO, then they do become mandatory. In order to avoid duplication of standardization work, it was decided in 1991 under the Vienna Agreement that when SEN and ISO both require a standard in a particular area, they would cooperate and not compete. So there has been collaboration between SEN and ISO in the preparation of various standards to support the Eurocodes. A very large number of supporting standards for Eurocode 7 have been prepared collaboratively by the following SEN and ISO committees. The SEN TC 341, Geotechnical Investigation and Testing, and that publishes, for example, EN ISO 22477-4, testing piles dynamic load testing. I should really have included, apologies to to Mike there, I should include 22477-10, which is the rapid pile load testing. ISO 178 Geotechnics, standards for the identification and classification of soil, and some supporting standards being prepared by just CEN with no ISO involvement. So you got TC 288 with a lot of execution standards for special geotechnical works, and then TC 396 with standards for earthworks. In 2003, the Commission published Guidance Paper L, listing the intended benefits and opportunities of the Eurocodes as being to provide common design criteria and methods and a common understanding regarding the design structures, to facilitate the exchange of construction services, marketing and use of structural components and kits, and the marketing and use of materials and construction products. They were intended to be a basis, to provide a basis for research and development. They allow for the preparation of common design aids and software, and they increase the competitiveness of the European civil engineering firms, contractors, designers, and product manufacturers globally. So those are the benefits of the Eurocodes, as seen in this guidance paper L. So moving on then, look at the regulatory background to and Irish standards. In order to further its objective of removing the technical barriers to trade in construction products between the European Union member countries, the Commission passed the Construction Products Directive in 1988. And this sought to ensure free movement of all construction products within the European Union by harmonizing national laws with respect to the essential requirements applicable to particularly health and safety. And the essential requirements to be achieved in the case of structures include that they shall have acceptable mechanical resistance and stability and are safe in use and in case of fire. The Eurocodes serve as a means to prove compliance of building and civil engineering works with the essential requirements of the CPD. So the Eurocodes serve to prove compliance. The CPD was repealed then and replaced by the Construction Products Regulation in 2013. An EC directive is a legal act of the European Union that requires member states to achieve a particular result without dictating the means of achieving that result. Whereas a regulation is an act of the European Union that becomes immediately enforceable as law in all the member states simultaneously. So they're different emphasis, different structure to them. Regulation can be adopted by means of variety of legislative procedures depending on their subject matter. And the reason given for the change was to simplify and clarify the existing framework and improve the transparency and the effectiveness of the existing measures. In order to implement in Ireland the Construction Products Directive published in 1989, the first Irish building regulations were published in 1991, with the latest update in 2021. And the stated aim of the building regulations is to provide for the safety and welfare of people in and about buildings. So it's similar to the bylaws. They apply to the design and construction of new buildings, including a dwelling, of a new building, including a dwelling, or extension to an existing building, and requirements for foundations of buildings. Since the Eurocodes have not been published in 1991, they are not referred to in the 1991 building regulations or associated technical guidance documents. However, they are referred to in the current 2012 technical guidance document A to the current building regulations, which states the use of the Eurocodes referenced in this document is a practical guidance on meeting the requirements of Part A. So when work began on the Eurocodes, Ireland didn't have a dedicated national standards body, as I mentioned at the start of the lecture. To oversee the development of the Eurocodes from an Irish perspective, the National Eurocodes Advisory Committee, NEAC, was established. And the chairman of NEAC until 1994 was Nick Ryan of An First Ferguson. Eric Farrell and myself, following their work on Eurocode 7, were invited to be members of the NEAC in 1986. And Eric then was appointed as the Irish representative on the SE7 committee in 1990. In the early 1990s, work took place to form the National Standards Authority of Ireland, NSAI. As a result, in April 1994, Douglas Burns from the embryonic NSAI was appointed Secretary of NEAC, with Jim Harrington as chairman. In 1996, the National Standards Authority Act was passed, and then NSAI formally came into existence in April 1997, as Carl mentioned in his introduction, and it became the Irish member of ISO and CEN. Barry Smith then from NSAI took over as Secretary of NEAC from 1996 and was succeeded by Yvonne Wild in 2013. And she established the Eurocode's Consultative Committee, EEC, in TC15 in 2013 with Jim Mansfield appointed chair. And then Ken Murphy, who's here this afternoon, succeeded Yvonne as Secretary of TC215 in 2018. So that's the sort of history and development of the Organisation of National Standards Authority in relation to Eurocodes in Ireland. A subcommittee of TC15 SE7 Geotechnics was established to monitor the development of Eurocode 7 with Eric Farrell appointed as chairman. And the main role of this subcommittee was to prepare a national annex for Eurocode 7 Part 1, giving the partial factors to be used with geotechnical designs in Ireland. Part 1 with the national annex was published in 2007 and was decided that no annex was needed for Part 2, which was also published in 2007. And TC15 has monitored and is continuing to monitor Eurocode 7, including the development of the second generation version. In 2020, David Gill, who's here also this afternoon, succeeded Eric Farrell as chair of TC15 SE7. Being member of CEN, NSAI publishes CEN standards as Irish standards with the prefix I.S.En, or in the case of an ISO standard, I.S.En ISO, when it's also recognized by EN. For example, Eurocode 7 Part 1 is, and the standard for dynamic testing of piles are published as I.S.En 1997-1 and I.S.En ISO 22477-4. NSA publishes now as Irish standards a very large number of CEN standards relating to geotechnical design, ground investigation and testing, execution of geotechnical structures and earthworks. As a result of that, there's rarely any need to refer to non-Irish standards such as British standards. Now, spread foundation design examples. Sorry, my lecture has been very non-technical up to here, so if anyone would like a bit more technical detail, hopefully it'll be in the paper afterwards, and I can add more detail to that. So I'm going to look now briefly at a spread foundation design example. Taking a spread foundation there, square one with width B, embedment depth D, it's carrying a combination of a permanent load and a variable load, and the central variable load is 0.25 of the permanent load, and the maximum allowable settlement is 25 millimeter. Characteristic values, the ground properties, C of 0, phi 35, and gamma of 22, E value of 20 GPa, and we're looking for the foundation width to satisfy both the ULS and the SLS. So using the bearing capacity equation given in Eurocode 7 and the factors in that that go with the equation, and also the partial factors from the Irish NA for all design approaches. These are the results that were obtained. So you can see here, you have those curved graphs are the different bearing capacity equations. There's my, so you see this, the lowest one here is for DA2. The next one up is for DA1, a DA1 combination 2. And the next one, as I find dots there, is for DA3. And then the top one is for traditional dying with a factor of safety of 3. And I've got another line here, the brown line, or that line, it's for foundation design for serviceability, for settlement. Now you'll see that over here, these lines are above the settlement line. So therefore the this is the foundation width. So if this is the design requirement for ULS, this is the design requirement for SLS, over here, the ULS controls. Whereas over here, the settlement is higher and the bearing capacity is less, so therefore the ULS controls. So therefore, ULS controls over here for foundation widths for lighter loads, and SLS controls over here, foundation controlled by SLS for larger loads. And that's because a larger volume of ground is loaded, leading to increased settlements. Now, looking at the divided between the two, you see the change from one situation to the other varies. So that line DA1, over here, ULS, over here, SLS controls, and the value of that is about sort of just under 900, 850 maybe kilonewtons there. I haven't given any units, must do that. The next one, a bit lower, is DA2. So the changeover from ULS to SLS occurs at a slightly lower value, and for DA3 it occurs at a higher one. And then for the traditional design, it occurs even higher again. It occurs up here. So therefore, traditional factor of safety 3 gives the largest width and hence the least economical design. So if you're comparing them, the least economical is the traditional design using a factor of safety of 3. If you're using any of the other designs, you're going to have a more economical design, designing to Eurocode 7. So Eurocode 7 probably has brought in more economy into designs, certainly in foundation designs. Now let's look at the second generation of Eurocode 7. CEN regularly reviews and updates its standards. In 2014-15, a systematic review was carried out of all the Eurocodes, and arising from this review, it was decided to prepare a second generation with the following priorities. They want improved ease of use. They were considered not easy to use, the first set. Increased harmonization. These weren't harmonized enough between each one, and a reduction in national parameters. And strengthening of the requirements for robustness. Robustness is a requirement which is a sort of buzzword in the Eurocodes. It wasn't, these are additional measures carried out to protect against unforeseen events and hence further ensure the safety and reliability of designs. So the things over and above what you calculate usually. And we look at what some of those measures might be. Following additional priorities were identified for Eurocode 7. Simplifying of the design approaches. And what's been done is they've turned it into design cases, being combinations of partial factors rather than having the design approaches, which was considered complicated or not very friendly before, user-friendly. Reorganizing of structure and presentation. So they're now more consistent. So all the Eurocodes are very consistent in the way they're set out and structured. Better alignment with EN 1990. So there's very close linking to EN 1990. Previously, it wasn't so linked to it. Improved reliability discrimination. It wasn't so linked to it because EN 1990 was really set up for structural design, not for geotechnical. But EN 1990 is developed now to be both for structural and geotechnical, and hence it's easier for Eurocode 7 to be linked back to it and made consistent. So that's been a great improvement. And more reliability discrimination, and I'll come to that in a minute. Improved rules for groundwater pressures, improved rules for common geotechnical structures, and more calculation models are included now. So there's much more calculation and assistance in it. And then improved rules for numerical methods. That's because more analysis is numerical nowadays. So more on that. And improved rules for design involving rock and dynamic design. Now, reorganization of Eurocode 7 geotechnical design from 2 into 3 parts. So it's been, previously we had 2 parts, now we're going to 3 parts. The first one is general rules and it has various things in it, but the main thing is the reliability differentiation with groundwater pressures, numerical modeling and alignment with EN 1990 as part of this improved part 1. Part 2 is has the concept of the ground model, which is a new thing being brought in. More focus on derived values and how to get them. Alignment with TC 341. These are all the testing standards. And then part 3 is the actual geotechnical structures which are designed. And the first 3 parts are more specific, like parameters and definitions and things. And then you've got 5 sections there, 4, 5, 6, 7, and 8, slopes, spread foundations, pile foundations, retaining structures and anchors, which are similar to which are in the existing Eurocode 7, but expanded and improved. And then 9, 10, 11, and 12, which are all new. New sections have been brought in to broaden the Eurocode, looking at fill structures, reinforced elements, ground improvement, and groundwater control. So those are new in the Eurocode, in the second version. Now, the second generation version of Eurocode 7 is 34 references to reliability, whereas the existing Eurocode 7 has just 5. So there's been a great movement towards reliability. And what is reliability? Well, Eurocode 7 or EN 1990, this is the second generation of EN 1990, says a structure should be designed and executed in such a way that it will, during its design life, with appropriate degrees of reliability and in an economical way, sustain all foreseeable and specified actions. And this second generation, 1990, gives target values for the reliability index related to the probability of failure for different consequence classes. And those have been mentioned earlier too. Mike mentioned them in his lecture. However, it's not expected that the beta values there, the reliability index values, will be used for geotechnical design. They're mainly intended for code calibration. But what Eurocode 7 says is that the verification of limit states by any of the methods given in paragraph 1, in other words, the calculation, testing, prescriptive rules, and observation method, shall provide a level of reliability no less than that required by EN 1990-1. And it further says that if you design according to Eurocode 7, 1997, you will achieve the reliability required in EN 1990-1. Now, reliability differentiation is defined in the 1990 as measures intended for the socio-economic optimization of the resources to be used to execute construction works, taking into account all the expected consequences of failure and the cost of construction works. And it requires structures to be classified into geotechnical categories that combine complexity of the ground and ground structure interaction, that's the Geotechnical Complexity Class, GCC, with the consequence of failure, in other words, the consequence class. And currently that's classification into a design of a geotechnical category. It's optional. However, in the second generation, it won't be optional because it'll be a requirement through this reliability differentiation. Now, Eurocode 7 states that geotechnical categories should be used to specify the extent and amount of the following measures to ensure the appropriate reliability is achieved. And these include measures to achieve appropriate representation of parameters for design and validation from the ground investigations design model, measures to achieve accuracy, measures to prevent errors in design and execution and the occurrence of gross human errors, and then they include designer qualifications and experience, quality management measures, and the amount and type of reporting, and measures to ensure appropriate implementation of design, including supervision, inspection, monitoring, and maintenance. So those are the measures to ensure you get the reliability required. Now, assumption of the current Eurocodes in Annex B of 1990 is that the personnel responsible for the design of a structure should have appropriate qualifications and experience. However, it doesn't state what constitutes appropriate qualifications experience. That has to be determined nationally. Now, Fintan Buggy, was mentioned earlier, led a drafting of Annex D for Eurocode 7, giving minimum qualifications and experience for different geotechnical categories. And this led to much debate within the Eurocode community as to whether it was appropriate to specify qualifications and experience in design codes. Now, following a vote by the SEN members last November, it was decided to retain Annex B in 1990, but to reject the inclusion of specific requirements in Annex D of Eurocode 7 and the other Eurocodes when the second generation comes along. So at present, the Geotechnical Society of Ireland and Engineers Ireland support geotechnical engineers applying to register their qualifications and experience with the UK-based ROGEP, Register for Geotechnical Engineering Professionals. And Carl mentioned that earlier, the roadmap. The key dates, now this will probably be interesting to people. Key dates for the preparation and issue of second generation of Eurocode 7 are the following. Well, between October 2020 and January 23, these SC7 task groups have been set up to review the documents, prepare design examples to test its code and its ease of use, and to prepare guideline documents. November 2021, the latest draft documents of parts 1, 2, and 3 were issued. I think actually since then, a more recent draft has been issued, but it's a moving target. September 2022 to December 2022, the PREN will be issued that's an inquiry period, and they be available for public review. And as Ken was mentioning to me over the coffee break, that's going to be a very busy period. September 2022, that's September this year to December this year, we'll have to read through the PRENs and decide what we like, what we don't like, and send in our queries. So it's a very short window in which to do that. Then January 2023 to March 24, the comments will be there'll be comment resolution, text finalized and translated. Then April 24 to June 24, there'll be a formal vote on EN 1997. And then in March 2026, all Eurocode parts are to be available to the national standard bodies for them to prepare the national annexes. So that becomes another busy period. NSA are going to have to prepare national annexes for parts 1, 2, and 3 of Eurocode 7 in that period. Now, 30th September 2027 is the last date for the national standard bodies to publish the second generation Eurocodes with the NSAIs, leading to a coexistence period. So you have a coexistence period between when you have the new standards with their annexes, and also you have the existing standards in parallel. And 30th of March 2028 is the date of withdrawal of the existing Eurocodes and the implementation of the second generation. So that's when we change over to the new version, 2028. And countries are free to publish the Eurocodes with national annexes whenever they're ready. Some may publish earlier than others, and some countries may publish all the Eurocodes at the same time. That's the Big Bang approach. And NSAI publish all the second generation Eurocodes at the same time. There'll be a coexisting periods when either version may be used. Now, the 6-month period, which is the minimum given, October 27 to March 28, is very short. So NSAI is planning a coexistence period of 12 months. So it aims to publish the Irish versions of the Eurocodes with their national annexes by March 2027. So it'll be 6 months ahead of the minimum of the last date for publishing it. So that's the deadline. So I'll finish up now with a few conclusions. How has geotechnical design in Ireland and Europe advanced with Eurocode 7? Well, I started off looking at the situation before Eurocode 7. There were no standards, no Irish standards, no dedicated national standards body here. British codes of practice were used, separate codes for different geotechnical structures, no consistency between structural and geotechnical design codes, and only bylaws in 3 urban areas with regulations for geotechnical design. And the European countries all had their own standards based on national practices and ground conditions. So the situation regarding geotechnical now in Ireland and since Eurocode 7, it's been harmonized with all the 10 countries using the same code for geotechnical design published as their national standards. Geotechnical design has been harmonized with structural design through the adoption of a common design language in the limit state design method and consistent safety requirements and partial factors. And Eurocode 7 provides a single code for all the different types of geotechnical structures rather than separate different codes for each geotechnical structure as formally. And Eurocode 7 is supported by a large number of 10 standards for ground investigation, testing, execution of geotechnical work. And other advances and benefits of Eurocode 7, it provides a definition for the value of a geotechnical parameter to be selected for use in design. And that's a novel feature. It's a flexible code, going back to what Professor Nash said at the start, allowing more materials or resistance factor approach within the limit state design framework. It uses geotechnical categories to specify the following measures to ensure the required level of reliability is achieved. So you get the appropriate parameters, you have accuracy in your calculation models, maybe model factors from the pile design should be giving you the correct calculation models. Errors in design and execution are prevented, hopefully, and you've got appropriate implementation, hopefully, through the measures. It's accommodating scientific advances in numerical analysis, reinforced fill structures, and ground improvement. It has brought together a large number of geotechnical engineers from across Europe in the development of Eurocode 7. And it's facilitated Irish geotechnical engineers to work in Europe and European engineers to work in Ireland. So on that, thank you for your attention.